I'm going to present our paper, Side-Channel Assisted Reverse Engineering of Encrypted DNN Hardware Accelerator IP and Attack Surface Exploration. I'm Cheng, currently employed as an offensive hardware security researcher at NVIDIA in Santa Clara. This work was completed during my PhD studies at Northeastern University. All opinions are solely my own and do not represent the views of my employer. Given the selection of paper of this conference, it's likely that many in the audience come from a software security background, while this work focuses entirely on hardware security, specifically on physical side-channel attacks. The concept should still resonate. The fundamental idea behind this attack is that every implementation leaks information through physical means. For instance, when the same computer program processes different values, the electromagnetic emissions can vary slightly. By carefully manipulating the input and using statistical methods, we can extract sensitive information by measuring these EM emissions. For deep neural networks, the most sensitive information includes the model parameters, weights, and biases. Previous research like CSN neural network showed that it is possible to extract such parameters using electromagnetic side-channel attacks. However, that was done in an academic setting targeting microcontroller units. Real-world DNN accelerators are much more complex because they need to handle increasingly large DNN models. These accelerators operate at high frequencies, using advanced technology nodes, prioritize power efficiency, and perform highly parallel calculations. Each of these factors leads to a lower signal-to-noise ratio, making side-channel attacks more difficult. This brings us to the motivation of this study. Is the signal-to-noise ratio so low that side-channel attacks are not feasible at all? In our study, we focused on the AMD Xilinx DPU, one of the most advanced DNN accelerators out there. Our thinking is simple. If we can break its security, then other, less advanced accelerators should also be vulnerable. The DPU is incredibly efficient. For example, when running ResNet 18 on the ImageNet dataset, it uses only a fraction of the power compared to the GPU counterpart. It also offers an end-to-end development flow. Developers can train models using familiar tools like TensorFlow or PyTorch. The DPU framework will automatically quantize the model with minimal accuracy loss. This shows just how advanced DPU is. The company behind it was acquired by Xilinx for about $300 million. The DPU is also a black box, with its valuable IP encrypted and tightly guarded by Xilinx. This makes it a perfect target for study, as we aim to assess the security of the top-of-the-line DNN accelerators. Let's jump directly to the conclusion. We can recover the parameters. However, there's a catch. We must reverse engineer it first. To understand why, we need some background information about side-channel attacks. The effectiveness of EM side-channel attacks relies on a fundamental principle. EM emissions are influenced by system operations and the data being processed. To illustrate this, look at the first figure on the right, which shows a simple EM analysis against the ECC cipher. In this scenario, we use a single EM trace. You can see that the EM emissions amplitude is drastically different when processing the values 1 and 0. Now, let's shift our focus to the correlation EM analysis, CEMA. This method allows us to extract the secret key from multiple EM traces. We model EM emissions as a combination of the selection function and Gaussian noise. The selection function V links EM leakages to data by calculating a predicted EM emission based on the input value and the secret key byte. To retrieve the key, we try all possible key guesses and compute the Pearson correlation coefficient for each generated predicted power consumption and the measured EM emission. With the correct key, it's identified when the result in the highest correlation between the predicted EM emission and the measured EM emission. For ciphers like AES, we do not need detailed implementation specifics and can focus on individual key bytes. This is partly because icebox using the cryptographic algorithm is highly nonlinear, making the selection function diffuse enough for analysis. However, when we turn to DNN CEMA, the scenario changes significantly. We cannot use the same approach here. For DNN, if we target individual multiplications and use a selection function, for example, the Hamming weight of the input times weight, we face a challenge. For example, secret weights 2 and 4 will result in the same selection function. This phenomenon is known as aliasing, where many secret weights has an identical selection function. In our analysis, we found that this aliasing affects 191 out of 260 weights, which is substantial. To tackle this, we need to shift our strategy to a Hamming distance model. This approach requires a detailed understanding of the data flow and scheduling within the system. For example, we need the exact sequence and the timing of input 1, input 2, weight 1, and weight 2 to extract the two secret weights. These are the reasons we need to reverse engineer the exact schedule of the DNN accelerator. We developed a comprehensive reverse engineer flow primarily using EM side channel analysis. This is the most substantial part of our study. For details, please check our paper. It's really interesting. Here's a high-level intuition of our reverse engineer flow. Since deep neural networks computations are too large to fit on silicon, the DPU used multiple layers of scheduling to divide the computation into manageable segments. Within each segment, there's a dedicated and complex scheduling to achieve high efficiency and data reuse. Here's a glimpse of our reverse engineering result. We use a configuration with 200 DSP slices for the MAC tile and 80 DSP slices for the ACC tile. Each MAC tile has 4 DSP slices, and each ACC tile contains 16 DSP slices. The architecture leverages 3 levels of parallelism. MAC tiles are arranged into 5-byte matrices, and each column handles 1 input channel, and each row processes 2 filters in a time-multiplex manner, showcasing the output channel parallelism. Additionally, each MAC tile can process 8 input channels simultaneously, demonstrating pixel-level parallelism. The convolution process involves 2 steps. First, in the MAC tile, the inputs are multiplied by 2 weights and accumulated along the input channel dimension. Then, in the ACC tile, these values are summed into the output feature. In our study, we have reverse engineered the schedule for each register within the DPU. While this table displayed here details the value for each VIP slice in the MAC tile across various clock cycles. We'll keep our discussion at a higher level to maintain clarity during this presentation. The fruit of our reverse engineering efforts is a cycle-accurate and register-accurate simulator of the DPU's computing arrays. This tool has been instrumented in our analysis, allowing us to pinpoint with precision which parts of the DPU are susceptible to the parameter extraction attacks. Interestingly, it's the accumulation tile specifically where the vulnerability lies. With the help of the simulator, let's walk through the parameter extraction attack. Our methodology is as follows. We begin by setting only I0, I1, and I2 into non-zero values, while all the other inputs are set to 0. This setup ensures that within the ACC tile, there are just 3 accumulations involving in a non-zero operand. At the second accumulation time point, we employ the concept of Hamming distance to decipher weights W1 and W0. We do this by analyzing the Hamming distance between the result of the first and second accumulations. Following this, Weight 2 is recovered by examining the Hamming distance between the third and third accumulation results. To extend this technique to other weights within the kernel, we selectively assign non-zero values to certain parts of the input. This selection multiplication allows us to isolate the recover additional weights systematically. Once we have successfully retrieved all the weights from the first layer, we can progress to the subsequent layer. Here, we utilize the SMT server to generate the input patterns required for the recovery. This process illustrates a systematic approach to dismantling the network layer by layer, showcasing the potential for comprehensive parameter recovery attack. To conclude, we successfully reverse engineered the data flow and scheduling of AMD Xilinx DPU and built a cycle-accurate and reverse-accurate simulator. The takeaway is that valuable DNN accelerator sub-IPs demand protection against soft-channel assisted reverse engineering attack. And utilizing the reverse engineering result, we have demonstrated practical attack on a real DNN model. This shows that, although challenging, a competent adversary can recover the complete DNN model running on the state-of-the-art commercial DNN accelerator. Thank you.